Hey class, welcome back. Electromagnetics. We're going to continue our talks on waveguides and extend this to rectangular waveguides and cavity resonators. First, a quick historical background. This gentleman studied at this place. I'm not even going to try to pronounce that one. I'm sure I would mess it up. He worked in engineering for Vindy, Drome, and others. This is an image of this gentleman, and his name is Augustin Jean Fresnel, lived from 1788 to 1827. Some notable things about Mr. Fresnel. He invented the Fresnel lens, which this is used in lighthouses to this day. It helps to disperse the light, certain type of lens. He developed the Fresnel equations on waves and reflectivity, which form the basis for many applications in computer graphics. So if you were to continue on in study of electromagnetics or even computer graphics, you would likely encounter these equations, or maybe you already have. He did a tremendous amount of work on the polarization of light, which you should now have a little bit of an understanding of that. And he discovered that polarization could be explained only if light was entirely transverse. And so, in addition, you should have some understanding of what that means for a wave to be transverse. That is, the E and H field are transverse to the direction of propagation. And finally, he went on to use this explanation to explain double refraction. So what is double refraction, you may ask? I'm glad you asked. Let's look at that. So around the time of Fresnel, a substance was discovered in Iceland. It's known as Iceland spar or crystal. We know it today by its scientific term, which is calcium carbonate. And so this substance had a very unusual attribute. The material that nobody could explain, and that was that it created a double image. So you can see here, let me get my laser pointer going. Forgot to do that. You can see here that if we were to put something behind a block of this, you'd actually see a double image there. Another example here I found on the internet, a piece of this calcium carbonate. You can see the graph paper is obviously double imaged there. For the longest time, people couldn't explain this, and it kind of bothered them, I think, that they couldn't figure it out until Fresnel. So, like I said, until Fresnel came along, and he was able to explain this. And so what he discovered was, through his study of polarization, was that this substance has a characteristic which we refer to now as being birefringent, and that means that its effects on light depends on the direction of the light, or the polarization, or the orientation. And so what would happen is we'd have this electromagnetic field come and hit, and so the electric wave would be bent at one angle, and the magnetic wave bends at a different angle, and depending on if it's parallel or perpendicular. And so this, of course, is what causes that. And so you still get, even with either the electric or the magnetic, you still get a bit of an image because it's still in the wavelength of what our eye can detect. But as you could see on the images before, that it is a much lighter image because you don't have both contributions from both fields for both polarizations. So as I said, we're continuing on in part 8 of the course, and we're looking at rectangular waveguides and cavity resonators. So far, we've restricted our discussion to parallel plate waveguides, and this, when we do this, it limits us to TEM, 0 propagating waves. We did this by strategically placing conductive plates at x equals 0 and x equal a, such that a, or the distance between the two plates, are half wavelength multiples apart. So if we now likewise strategically place two more conducting plates at y equals 0 and y equal b, so you see up here they're separated in the x direction, here they'll be separated in the y direction. And again, make sure that these stay multiple half wavelengths. We could then have simultaneous propagating modes between these plates, so all 4 plates at the same time. And so when this happens, we denote this as TEM, N, where M is on the X direction and N is in the Y direction. When we do this, this type of structure is known as a rectangular waveguide. We'll look at a picture of this on the next page, but these are still in use today. A lot of microwave transmissions, which are still used in cell phone technology, utilize microwave transmission, and we use microwave antennas. This is what this structure would look like then if we have our X, Y, and Z origin at this point or this corner. You can see that in the X direction, the top plate is at X equals 0, the bottom plate is at X equal A, and then likewise the plate that's facing us is Y equals 0, and then the plate that's on the other side here is at Y equal B. And so you can see this in relation to our EY, HY, and HZ wave directions. So with this type of structure, we can now have propagation components in either the X or the Y direction, or even better, we can do both at the same time. So the cutoff wavelengths for both the X and Y directions can be calculated by these equations here. So for the M, which are associated with the X direction, it would be 2A divided by M, which depends on which mode we're looking to propagate or how many half wavelengths. And then TEON would be 2B, which is in the Y direction, divided by how many half wavelengths we want in that direction. So let's look at see what that looks like. So in our waveguide then, if we have our M modes, you can see that it's just bouncing back and forth between the plates in the X direction. And so here's a side view of that. So it's kind of just, if it's coming at us, it's just going up and down. For the N modes, it's going back and forth horizontally between the Y plates. And so if we were to look at that coming at us, then it's going to just be going back and forth. So when we have both propagating at the same time, it kind of starts to make a corkscrew motion down the waveguide. And so if we were to look at that, then coming at us, it would look like it's ricocheting off each side as it comes toward us. So when we have propagation in both directions, the cutoff wavelengths then are related by this equation here. So our cutoff wavelength squared for the TEMN mode is going to be 1 over 2A divided by M squared plus 1 over 2B divided by N squared. Or we can flip that over and have this equation. So likewise, this entire derivation can be applied to the magnetic field as well. So these are for TE modes, remember. So this is for our electric field component. We can do the same thing with our TM mode. So we can actually have E fields and our electric fields and magnetic fields, multiple modes propagating all at the same time. One thing to note though is when we have magnetic modes, both M and N must be non-zero. You cannot have a TM01 mode or a TM10 mode. It has to be at least 1-1. These cannot be 0. Whereas on the TE modes, you can have TE10 or TE01. So let's look at some examples of how this works then. It's desired to determine the lowest 4 cutoff frequencies referred to as the cutoff frequency of the dominant mode for 3 cases of a rectangular waveguide. And so we'll have the case of where the ratio of the X and the Y sides is 1, the ratio of the X and the Y sides is 1/2, and that ratio then again is 1/3. So given that A is equal to 3 centimeters, it's not a very big waveguide, it is then desired to find the propagating modes when we are transmitting at 900 megahertz for each of the 3 cases. So to do this, we first recall that the cutoff wavelengths can be calculated using this new equation that we've derived. And so likewise, the cutoff frequency then is given by the phase velocity divided by the cutoff frequency. And so when we do that, this is plug those numbers in, this is what we come up with. So one thing we can do then is we can pull the A term out, since we are given A, and then you can see it's the number of M modes in N times the ratio of A over B squared. So from this, we see that the cutoff frequency of the dominant mode, that is the TE10 mode, is 1 over 2A square root of the permeability and permittivity. So that being the case, we can now come up with this ratio of the cutoff frequency divided by the cutoff frequency of the dominant mode is equal to just M squared plus N over AB squared. So this simplifies the math a little bit. This also takes out of the equation or our calculations the permittivity and permeability. And another reason that this is one way we usually look at it is because until we hit this dominant mode, there's nothing propagating, right? So we really are only become interested when we hit that first dominant mode and things start propagating. So this ratio comes into play then. So by now assigning different pairs of values for M and N, we can determine the lowest 4 values for this ratio for each of the 3 specified conditions. And so we can graph those on the following slides, but we usually look at this. So this is how this looks. So again, moving along this axis, it's our ratio of FC over FC TE10. So of course, when this is equal to 1, we get, since it is both sides are equal, or A and our B would be equal, TE10 and TE01 are both going to propagate at the same time at this 1 value. So when we get up to this ratio being square root over 2, we'll find that our TM and TE11 modes both start propagating. When we get up to twice this dominant mode cutoff frequency, then our TE20 and our TE02 modes. And then when this ratio gets up to the square root of 5, you see all these modes propagate. Now if we come down to here where we have the ratio is equal to 1 over 2, so in this case we could say that if A was 3, then of course B is going to be 1.5 centimeters. We put that 900 megahertz down the waveguide. Of course we'll have our TE10 mode start at 1, but not the TO1. That doesn't happen until 2, and that's because these sides aren't equal, right? And so then we get up to square root of 5 again. We'll see we have these 1-1 modes start to propagate. We get up to square root of 8, then the 2-1 modes, so on and so forth. All right, and then when we go to 3 over 1, so now we'll have A is still 3 centimeters, B is 1 centimeter. Again, T10 will be the first to propagate. T20 will propagate when we get twice that cutoff frequency. When we get to 3 times that cutoff frequency, TE30 and TE01. And again, these are just going back and putting in the M and N values back into that original equation that we have for this ratio. So for A equals 3 centimeters and assuming free space for the dielectric and the waveguide, we can go back and calculate then that our dominant mode frequency is going to be that 1 over 2A times the square root of these values of the permittivity and permeability. So when we put those values in, we see that we will start to have the first mode of propagation at 500 megahertz. So for the frequency we're interested in of 900 megahertz, all modes for which this ratio is less than this 900 divided by 9,000 divided by 5,000, which is equal to 1.8, will propagate. So from the graph, we should be able to pick that off pretty easily. So we'll see for the ratio of B over A equal to 1. This will happen for these 4 modes. Looking back on that graph, for the condition where B over A is equal to 1 over 2, this only happens for the dominant mode, that we don't get up to the next mode before we hit the 900 megahertz. Same thing for 1 over 3. So this is how that works. This is how you can determine which modes are going to propagate. So the last thing I want to just touch on here is what we call a cavity resonator. So we've looked at when we put plates in the X direction, half wavelengths apart, multiples of. Y direction multiples of half wavelengths apart. So now what happens if we come back and put them in the Z direction? Well, if we do that, this will create a standing wave then in our cavity. So we now created this cavity. And like I said, in the Z direction, we'll have a standing wave. And so such a structure then, if we have this, is called a cavity resonator. So here's where we can resonate a wave, and we can actually keep pumping energy into it, increasing the intensity of this wave. And this is how we amplify microwaves. So these devices have several uses, one of which is the function of a microwave oscillator. And so this occurs when the D is equal to L times lambda G over 2, again, where the lambda G is the half wavelength of the propagating wave. And so this is the basis for what you might have heard the term klystron. And klystron is, of course, it's a little more complicated than this, but it is very similar. It's what's used in your microwave oven. So this is how your microwave oven is able to create, high wattage microwaves and to cook your food. So we can have different L values for the length of how far away those Z plates are. So when this condition is satisfied, we then have oscillation. So this happens then, the wavelengths that oscillates, the lambda oscillating wavelengths 1 over squared is equal to just the extension of what we had before, where we're adding the Z term over here at the end. Or, as we did before, we could flip it and take the square root, and so this just defines our oscillating wavelength. So this, we can extend this as well to get our oscillating frequencies. Again, taking the phase velocity and dividing it by this wavelength, and we come up with just the three-dimensional extension of what we looked at earlier. So a quick example here then, the dimensions of a rectangular cavity resonator with air dielectric. We have there A, which is the X direction, is 4 centimeters, B, which is the Y direction, 2 centimeters, and then D, which is the Z direction, 4 centimeters. And it's desired to determine the 3 lowest frequencies of oscillation and specify the modes of oscillation transverse with respect to the Z direction for frequency. So we can use this new oscillating frequency equation we just looked at and plug the values in. And when we do, we come up with this. So now we have this equation in terms of how many modes we're going to have, or that we want to look at. And so if we get it down to, we can bring all these numbers out and solve them. So now we have 4m squared plus 4n squared plus L squared megahertz. And so we can plug in different modes. So for this case, by now assigning combinations of integers for m, n, and L, and recalling that both m and n must be non-zero for Tm modes, we obtain the 3 lowest frequencies of oscillation. So when we get up to 5303 megahertz, our T101 mode will begin to oscillate. And some of this is done by trial and error. At 8385 megahertz, we'll have 3 modes that will propagate, 3 TE modes here. And then when we get up to 9186 megahertz, we see we have 2 more modes that will begin to propagate, the TE111 and the TM111. So again, remember all these have to be non-zero terms before we see that first TM mode.